A distribution of the data refers to the shape it's in when you graph it, such as a histogram. The most commonly seen and therefore well-known distribution of continuous values is a bell curve. It's also known as a normal distribution, because it's the distribution that a lot of data falls into. It's also known as the Gaussian distribution, more formally named for Carl Friedrich Gauss. Therefore, you'll see references to data being normally distributed, or Gaussian, which are interchangeable, both referring to the same thing, that the data looks Gaussian. Some examples of observations that fit a Gaussian distribution are the people's heights, IQ scores, and body temperatures. All right, let's jump over to some code and create a normal distribution. Running examples generates a plot of the idealized Gaussian distribution. The x-axis are the observations, and the y-axis is the likelihood of each observation. In this case, observations are around 0, 0. Observations around the 0 mark are the most common observations, and observations around the -3 and the +3 are rare or unlikely. Before we dive into important summary statistics for data in Gaussian distributions, let's generate sample data that we can work with. We're going to use the rand function in NumPy to generate sample distributions of data drawn from a Gaussian distribution. There are two key parameters that define the Gaussian distribution here. They are the mean and the standard deviation. You'll delve deeper into these parameters later, as they are key statistics to estimate when we have data drawn from an unknown Gaussian distribution. The rand function will generate a specified number of random numbers drawn from a Gaussian distribution with a mean of 0 and a standard deviation of 1. We can then scale these numbers to a Gaussian distribution or by choosing a rescaling number. This can be made consistent by adding the desired mean, for example, with a mean of 50, and multiplying that value by a standard deviation of 5. Running the example generates a dataset and plots a histogram. You can almost see the Gaussian shape to the data, but it's a little blocky. This highlights an important facet to distributions. Most of the time, the data is not going to look like a perfect Gaussian distribution, but it will have Gaussian distribution-like qualities. It's almost Gaussian, and maybe it would be more Gaussian if we plotted it a different way, scaled it in some way, or gathered more data. Often, when we're working with Gaussian-like data, we can treat it as Gaussian and then use all the same statistical tools and get reliable results. In the case of this dataset, you don't have enough data and the plot's blocky because the plotting function chooses an arbitrary size bucket for splitting up the data. You can choose a different, more granular way to split the data and better expose the underlying Gaussian distribution. Let's run the example and then bin our data into 100 splits. When we do this, we can clearly see it's a more Gaussian-like distribution. The dataset was generated from a perfect Gaussian, but the numbers were randomly chosen, and we only chose 10,000 observations for our sample. You can see, even with this controlled setup, there's obvious noise in the data. This highlights another important point, that we should always expect some noise or limitation in our data sample. The data sample is always going to contain errors compared to the pure underlying distribution.